So in the previous video we looked at the basics of what a equation for a wave or an object undergoing simple harmonic motion looks like, and we got to this point which was the displacement is the amplitude multiplied by sine and the angle in radians is 2 pi ft. So f being the frequency, t being the time, and 2 pi f is the angular frequency, which is what we use when we're dealing with simple harmonic motion. So for this video we're going to look at the equations of simple harmonic motion beyond displacement. So we're going to look at acceleration and velocity and where they come from. So the first equation I just want to go back to is one that I've just literally just put, which is angular frequency. So angular frequency, omega, is equal to 2 pi f, and obviously because f is 1 over the period, we can also have 2 pi over t. So that's the equation for angular frequency, the units being rad per second, as in radians per second, and as effectively a measure of how many rotations occur per unit time, or how many complete cycles in the case of an oscillation occur per unit time. So with a displacement time graph like we had a moment ago, if you think about a particle at some point on here, I'm just going to choose this point. Obviously at this point in time the particle has a displacement x of some certain value, and that displacement is positive. Now, because it's displaced from the equilibrium position, because the object is oscillating, there will be a restoring force acting back towards the equilibrium. And obviously wherever there's a force, there is an acceleration. So you can see that despite the displacement being in the positive direction, this acceleration therefore is in the negative direction. So this is an important relationship between for simple harmonic motion, and is our definition. So the definition of simple harmonic motion is that acceleration is directly proportional to displacement and acts in the opposite direction. So I want to prove that the equation that we just had for displacement, and we looked at in the last video, is a solution to this relationship. So I'm going to start with the equation. So x is equal to a sine, and I'm just going to keep it as simple as omega t. I could obviously put 2 pi f there for omega, but I'm just going to keep it as that. Now, in order to work out the acceleration from a displacement, acceleration is the rate of change of velocity, and velocity is the rate of change of displacement. So acceleration is displacement divided by time squared. So what I'm going to do is I'm going to differentiate this in order to get an expression for the displacement divided by time. Now, you are not expected at A level to be able to differentiate. I'm going to do this and just explain the result so that you can see where the result comes from. So we have dx by dt, which is the velocity, is going to be equal to, now a is a constant, so that doesn't change when we differentiate it. When you differentiate sine, that will turn into a cosine, and because we're differentiating it with respect to time, the time isn't factored into this, but the omega will be taken outside the bracket. So what we're left with is omega is a, because that just stays the same, cos because we've gone from sine to cosine, and omega t ultimately stays the same inside the bracket. So just what happens, just two simple results, is that the omega comes outside the bracket, and sine gets turned into cosine. So that's when we differentiate it once with respect to time. So that is equal to the velocity. So this gives us an equation for velocity, because I said in the previous video that this here, a cos omega t, was also a possible equation for displacement. So velocity is equal to omega x. So simply the displacement times the angular frequency. So if we differentiate this again, so we do dx by dt squared. So I've differentiated x with respect to time twice, so I've differentiated this again. The same pattern happens again. So omega is taken out, so I then get omega squared. The a is still a constant, so that stays. Obviously the previous omega is a constant now, so that stays. So it's just taking this out and adding it to that. And when I differentiate cosine, it goes back into sine, but if I differentiate cosine, I get minus sine. So it's minus sine, and then inside the bracket stays the same. Now if you look carefully at this, you'll see that this bit here is the same as our displacement at the start. So since this is equal to acceleration, we get that acceleration is equal to minus omega squared x. And so from this you can see a is directly proportional to displacement and acts in the opposite direction, and the constant of proportionality for this is omega squared. So another way of writing that equation would of course be a is equal to minus brackets 2 pi f all squared x. Now there is one extra sort of special case of each of these that you should be aware of, which is the maximum velocity and the maximum acceleration. And in that case, the displacement just happens to be the maximum, which is the amplitude. So the equation for the maximum velocity is omega multiplied by the amplitude. And the equation for maximum acceleration, so I'm just going to write here, just running out of space, is minus omega squared a. So just the displacement is the maximum. So we have here our basic equation for displacement for an object undergoing simple harmonic motion. We then have our equation for velocity, acceleration, both maximum velocity and maximum acceleration, and we have our basic equation for angular frequency, and frequency being 1 over the period. So these are the key equations in simple harmonic motion that you need to be able to use. You don't need to be able to differentiate. You won't be expected to show this, but you do need to understand this is our definition for simple harmonic motion. Any object undergoing simple harmonic motion, the acceleration is directly proportional to displacement and acts in the opposite direction. And therefore, if you were to show this as a acceleration displacement graph, you would have a straight line passing through the origin, which represents the directly proportional aspect of this, and it would have a negative gradient to show that displacement acts in the opposite direction to the acceleration. So if the particle is displaced positively, the acceleration will act negative to return it to the equilibrium position.